Welcome. Today I will talk about, I know this is an AI conference, but as you can see today I will talk more about the brain. So I will talk more on the eye side, mostly about the brain behind the eye side, so because then you can develop better AI systems. And we will have a demo, but as usual, something is not working. Yep. Yeah. Okay, now it's working. So he said most about me. So I have more than 15 years of experience in both telecommunication and IT, almost 2 years in Atos right now. And so I'm started as the project manager, so now I'm the team manager. Last year I started my PhD. That's my second PhD. I started one when I was in Turkey, but then I moved to Poland, so that was not an accident. So and I had to stop it. That's me in the picture that you're seeing. That's my experiment when I was in the master's. I was working with schizophrenic back then. And other than about me is I'm trying to be free diver. I have, yes, neuroscience lab at my home. You will see a little bit of demo today with Carolina. I have like a separate EEG devices. Also, I started to do some CRISPR experiments, so I like some gene editing. I'm also the Neurotech AI podcaster, but that's, as you can expect, mostly in Turkish. So let's start with the brain. So I want to start with the neurotechnology because that's my field, how real brains merge with the AI. So I will start with a small video. This is the 2014 FIFA World Cup in Brazil, and I can see most of the audience is men, so you probably watched some of those games. That's almost 10 years ago. You can see that this kickoff was done by a paraplegic man. His name is Juliano Pinto. He was 29 years old at the time, and he cannot feel his lower trunk, which means that at the moment that he did the kick, he cannot actually move his legs. He did the kick only with his thoughts. So how this man performed the kick? So when FIFA announced that they're going to do the World Cup in Brazil, one of the distinguished neuroscientists from Brazil went to FIFA and said that let's do the kickoff with the paraplegic man. And as usual, they were like, do you know that the paraplegic means that they cannot move the legs, and football has the word feet in it. So we need someone who can kick the ball. But he was like, yeah, okay. And then he gathered like the team of 100 scientists. They worked like almost a year. And then they came with the kick. So before going to understand why this is very important, because this is for the neuroscience, is the moment like where you can see a small step for a man, but a giant leap for the mankind. Yeah. To understand that, we need to go back about the details. So I know that you're not into brain at all. I hope you will be. But yeah, let's go. It all started in 1924 when the German neuroscientist Hans Berger, he's the first person who recorded the brain waves, electrical signals in the brain. So as you can see, when we are thinking, we're moving, we're doing anything, so the brain produces electricity. That is 24 hours a day and then 7 days. So it never stops. Unless you want to do the presentation, then it stops. Then you need a brain. So yeah, he recorded the brain waves. This is an actual new Christmas card that was sent to his friend. So you see, there's a Christmas wishes in here, and you see the device attached to his mind. So that's actually the EEG. It records, it gathers your electrical signals, and your electrical signals has the data of the speech, has the thought inside of it. So the idea of the AI in the brain part is that you need to find that signal, because when you have this mixed signal, right now, well, I'm talking, it's in there. I'm thinking, I'm listening, I'm walking, I'm moving my hands. They're all embedded in the same signal. So you have to find the one that is the correct one, and you have to capture that one. And that picture shows that. So the brain works with electricity, But the video comes with the idea is from the Jacques Vidal, so it's his papers on the top. So he asked this most famous question. He said that, can we control the machines just by thinking? And it seems like, I'm sorry, I'm not very used to those kind of things. So yeah, it seems like there was 50 years between two things, and it seems like a very basic question, because the idea in his mind is, okay, so when we are thinking if the brain produces the electricity, so if the machine is working with electricity, can we somehow capture the signal from the brain, amplify it, and just make the machine work? And yes, that was correct question. 50 years for a long time, but correct question. So the next ones are not so very much for you. So in 1980s, animal experimentation started, because whatever you want to do with the brain, first you need to try in animals before in humans. And then 1999, it was first time used, and 2015, IBM's Blue Brain project started. So if you go back to that one, let me put it. Okay, so he wears an exoskeleton, which means outside skeleton. But the thing is, it's not exoskeleton that lifts him up and makes him move. So as you can see in this blue helmet in here, it has the EEG, and I brought one in here, and we will try with Carolina. So what an EEG, maybe Carolina, you can come here too. Yeah, thank you. So what I will explain in the meantime, what an EEG is, I have 5 signals probes in here. So when we put this into Carolina's mind or anyone's mind, so it captures the signals from the front end. And this one for Juliana Pinto, it has his whole hand, his whole head. So it gathers the signal, but the interesting thing is, so he was thinking about moving, because right now we know that when you're moving your arm, let's say, or when you're closing your eyes and thinking about moving your arm, the brain produces the same electrical signals in the same spot. So what he was doing is he was just thinking about moving and kicking the ball, and that's how he did it. And you see his... Okay, that's nice. Okay, now there's time for this demo. Let's see. So what we are going to do, if this device is working, so can you please I will explain. One thing that brain data is also, from the health data, so it's very, from the GDPR point of view, we cannot see that. But what we are going to see is the alpha brain waves, which shows the relaxed calmness. Okay, you didn't see the first section. So right now, the device is calibrating. Can you please sit? Yeah. Calibrating based on her brain signal. So because the brain waves is like a fingerprint, it changes from the person to person. I'll make it a little bit silent, not from here. When the session starts, okay, let me pause it for a minute. So you need to understand what you hear in here. So the rain in here actually represents her brain signals. So whenever she was calm, we will do it like a minute for you, but she'll do it for 15 minutes. Whenever she was calm, you will see the rain just lowers, and if she's really calm, there will be some birds in the background. But whenever she gets anxious or stressed, then the sound will be higher. It's like real rain. So you will understand that then the idea in here is actually you can play with your brain waves. So this is the neurofeedback. So once you hear your brain waves actually, so you can try to relax. One very easy step to relax is just closing your eyes. And we will do it with her, and then she will put the headphones, so we will continue the presentation. And at the end, you will see how much she relaxed or what points she was relaxed. So let's start right now. So she's not very relaxed. That's normal. Can you see? Now she's relaxed. Yeah, now she's not relaxed. So this is the brain waves. That's actually... Okay, that's actually what is happening behind her brain. So when she was like, when we are anxious, and like now it's in the stage, and that's a very normal moment to be anxious, her brain waves go crazy, and her alpha waves especially. So there are different types of waves. But when she closes her eyes, that's a trigger for the brain to relax, because that's how we went to sleep. And suddenly it goes like, it calms down, it lowers, and it's like, if we had a blood pulse monitor, we will see after a while that her blood pulse is also reduced. So what we will do is, I will give that to you. Okay. And she will put that so you will not hear it in the background. And she is not going to, yeah, that's okay, you don't need that anymore. At the end, you will need it. Yeah, you can, let's try. That's good. So, yes. Okay, so that is the FIFA, and that is the same mentality. So if he is generating the thought, this EEG device is like a very detailed, and her mind just captured the signal and then transformed. So that's the AI comes. So you have to find the perfect signal into the bunch of the other signals, and then transfer it to the exoskeleton, and exoskeleton lifts him up. And this one is, for me, very important slide, because this is, for me, how the journey started. This is my grandmother. She died like exactly 10 years before the kickoff, the symbolic kickoff. But the reason I put her is not because she was my grandmother. This is a very old picture, so beginning of 2000s, and like a couple of years before she died. And the reason is she had brain surgery like 7 or 8 times. And the picture is not very clear though, but in here, I don't know if you can see, but her head is a little bit not like, let's say, oddly shaped. The reason is because she has a growing tumor in her forehead. And at one point, the doctor said that this tumor is like the skull might be causing that, so they removed the skull. So at this point in this picture, from here to here, she didn't have any skull, so it is actually, her brain was there without any protection, like just one layer of envelope, and that was it. So she had that surgery at early age because her tumor started like when she was 30s. And for me, the interesting thing is, obviously, since she has no protection, and forebrain is, you will see the most important part, that is the one that creates the intelligence. So she has to be the protector, she has to be the skull of herself, so she cannot hit her head, she cannot touch her brain or her forehead, she cannot even lean forward, so because the brain is not attached to anything in the skull, so it moves backward and forward. But as a child, you know, like we were not allowed to touch it, but you know, like when she was sleeping, I was going in trying to touch and understand like what is the brain. So yeah. Don't worry, I was not the reason she died. Anyway, so she didn't know, because when she died, I didn't start at the neuroscience, but she was the actual reason that I got very curious about the brain, because I wanted to see what was there. Okay, so now what the brain is. So I will explain that to you. I will not go into detail because I know that that's not your topic. So brain has 2 hemispheres, left and right. So my right arm and right body is controlled by the left, and my left side controlled by the right side of the brain. And there is between right and left side on the bottom of the brain, there is a bridge. Yeah, there are connections of the bridges. And if you somehow cut this 2 brain parts separately, then your body starts to react differently, because then there's a control issue between right and left sides. And for me, the most important thing is evolutionary, how it evolved. The brain evolved from like an onion, from inner to outer, and from backwards to forwards. So in this picture, the brain stem, which we call as a reptilian brain, this is the first brain of the animals or of the creatures on the world. So that evolved 300 million years ago. What it was doing, it was maintaining these body functions, routing information up and down, because that's the sensory information that needs to go down. And it is the reason of the instinctive behavior. So that instinctive behavior means that your fight or flight response. So when you have a very dangerous situation, you either fight or you flight, so you run away. It all comes from your reptilian brain that's 300 million years ago. And that is the only emotion at the time. But then, like almost 100 million years, there is the limbic system evolved. So the second part evolved. We call it paleomammalian brain. This is animal needs. The emotions are there. So this is the place where we had our emotions. And as you can see, like there's a big gap between two brain evolution. For almost 100 years, the animals, or the animals, they don't need any emotion. And then they started to need emotion. So they had only one emotion, which is fear. So fear is basically our first emotion from the evolution perspective. We only fear of the things at the beginning. So it's a fear of that, it's a fear of hunger, so whatever you call it. But then the emotions comes, and the reason the emotion comes is because nowadays we are gathering the groups. So the only reason that you need emotions when you are more than one. And as you can see, this is 200 million years, is the time when the mammalians come to the earth. So they start to appear, and there is a baby, and there's a connection. So when there's mother and baby, even though the animals are not forming groups, they are already more than one. And emotions in here makes the sense that it is the first language. So even before our language appears, we talk, we communicated, or the animals communicated by their emotions. So that is the importance of the limbic system. And I think, and as you can see, that's 200 million years. So it's not like 1,000 years or 100,000 years. For 200 million years at least, these emotions are there, and we are communicating on the basic level with the emotions. Why I said that? Because I know that there's generative AI people speaking, working in here, or large language models. So if you want to create something, the next one is neocortex, it's cortex. This is the intelligence part. That is the part that everybody is working right now. But if you can see, it's like only 115,000 years old. So whatever you do, you need to go into the deeper brain. So if you think the brain evolution like 24 hours, the cortex comes on the 45 seconds. So the real control is back on the deep. So if you want to develop something that really, like some chatbot or whatever, so you are understanding why people are not trying to talk with the bots and want to go with the agent, it's because their limbic system. It's because the chatbot is cortex, but they want, at that moment when they're frustrated, they want their limbic system. Their limbic system was talking, actually. So that's why they want to go to agents, so they can yell or they can do whatever. So that is very important for that. The next one is the cortex, mammalian brain, and this is where all the humanity, as we call humanity, right now they appear. So it's our perception, planning, attention, whatever you do, it happens there. But as I told you, it's like it's 45 seconds, and right now it's like a noisy baby. So it takes over control of all your brain, but it's like a noisy baby. So let me give you an example from me. I am scared of the dentist. I am scared as hell. Like a couple of months ago, I need to go to the dentist to remove one of my teeth. And I was postponing it for almost like 10 years. I was like living with pain at one point so bad that I was like, okay, I'm still not going to the dentist. At one point I went, there was a root canal treatment, but it's still not working. Anyway, I went to the dentist, I'm stressed, and they have to remove my teeth. But this dentist is some person I know, so I'm comfortable. I'm supposed to be comfortable. And I was in the dentist chair. They do this injection, so I cannot feel anything. There's like no nerves there anyway, so I will not feel anything at all. But then my body starts to give some weird reactions, like I start to shake, I start to get stressed. And since I am a patient there, but my brain works in a more like a neuroscientist way. And at one point I was so stressed, it's not like stress anymore, it's more like a phobia. I start to shake, so some nurse had to come and hold my head. And when she did it, I start crying. And the doctor was like panicked and like, that's not normal. And I was, at the moment, I was like giving those reactions, and back of my mind, I was talking with my brain at the same time. Like, I was like, what the hell? Like, I'm not feeling any pain. So if there will be some pain, I would understand the reaction. But I was not feeling any pain at the moment. And I was like, dude, can you just like stop those reactions? So I'm not feeling any pain. Why you are giving that thing to me? But at the time, cortex, even though it knows that bastard, that knows that I have no pain or anything, but the reaction I gave went through all the way, not the limbic system, but my reptilian brain. So at the moment, the phobia is telling me that I have to, if I'm not fighting because I cannot fight, then I have to flight. So this is, the body gave me my reaction, my like starter to run away, just like elevates my heartbeat, shakes, telling me like, just run, just run. It's like somebody's captured you and they're trying to kill you. And even though I know it at the cortex level, that's not true. I went it voluntarily. I'm not feeling any pain. Since these are, like, as you can see, 300 million, so these are rooted very deep. So I cannot go anywhere. I didn't go, and I didn't stop. Even though all these moments I tried to understand from the neuroscientist point of view what happened, but I couldn't stop anything. So this is the very deep part of the brain. So as I told you, intelligence lies on the blue side, and but like if you lose some part of the blue side, it's not end of the world. And you can see it from my grandmother. When they removed the skull, they removed a part of the brain too from the forehead. Forehead is the part of the intelligence, but she was playing bridge till her last years. So brain is very adaptive. It can change itself, adapted to situation. So it doesn't mean that as long as there are a lot of studies, even you lose like half of your brain, your inside of the brain empty, you can still continue your life normally. So that is another thing. So it's the cortex. I told you, like whatever you do, it's like human, rat or mouse. So you have this cortex that makes you think. And then you have, like, as a humans, we have 86 billions of neurons. We're on the top of the pyramid. We are the most, as you know, we are the most intelligent ones. That's basically because of the neurons, number of connections, but mostly because of the number of connections. The interesting thing is you see is we have, as a fetus grows like 250,000 neurons per minute. So imagine if your brain develops in the same way, you already should have like the millions of neurons right now. But what we know that we're almost born with the same amount of the neurons. Like you can grow a little bit later, but you always grow with the same amount of neurons at the beginning. But what is not happening, like you just have neurons everywhere, it is the networks are not mature. And let me explain the detail in the next slide. So this is your neuron cells in the drawing. These are the actual images of your neuron cells. So as you can see, when you were born, there were a lot of them, and they were trying to make connections. So that's how you do the learning. So we call it plasticity. Every time you learn something, your neurons make a connection with each other and gather groups. So whenever you learn something new, and like that can be a language, that can be a music instrument, or that can be, even if you're brushing your teeth with your right arm, try it with your left arm for a while, the brain changes its connections. And every time you do something new, it gathers new form of groups. But if you're not using that connection, then it drops it. So this changes over your whole life. That means that your brain actually constantly physically rewires itself. So it's not the same brain as it was like 10 days ago, as it was like 100 days ago or a year ago. It always changes, so it rewires. So it's very alive, very dynamic, very movement. And I didn't say it in the beginning, but that's why it consumes like 20% of your body energy. So even though it's like 2% of your body weight. But so that is a very good question, because we know that as a neuroscientist, we know the brain changes its structure. But what does that bring us about the singularity? So singularity as I think most of you know, that the hypothetical point in the history, in technology, like especially in AI, where the where human potential, like this technology point, where AI reaches a superhuman level of intelligence and capacity. Sorry, I had to read that. So do you think that's possible, that AI can reach intelligence, human intelligence? And if we call about the human intelligence, then which human are we talking? So yeah, from neuroscientist point of view, that's not possible, because your brain rewires all the time, and you cannot have one brain, and you will also see that in the next slides. But I can tell you that that idea is also popular among the neuroscientists, because 10 years ago, a group of neuroscientists said that, yeah, we can simulate the human brain in a supercomputer. They gathered together, and 500 scientists, they got 600 million euros from European Union, so that's one of the biggest funds, and they started the Human Brain Project, and the idea is to understand the human brain and to model it in the computer. That started in October 1st, 2013, and that's going to end in October 1st this year. And they said that, no, we cannot do it. And the reason they cannot do it, because right now, as I showed you, it's impossible to model the whole human brain. Yes, they can model from temporal lobe. Temporal lobe is like the side of the lobe. They can model a part, or they can model some small animals, but human brain, if it's rewires, we call it plasticity, it changes itself all the time. So even though they had this amazing funds and amazing scientists, and this is on the European Union, then US started and China started, like at one point, the whole world was trying to do it for the neuroscientists, but they gathered the understanding that no, we cannot do it. It's too early for us to do it, because as you see, we record the first brain signal just 100 years ago. And there is 300 million years of structure rooted deep in the brain. So that brings me the other part. So the brain rewires itself, which means that you might expect the brain to behave in one way, but somehow it behaves another way. And that's this headline is brain's own point of view. That's a very new theory, because the scientists right now believe that the brain has its own point of view. So it's not tabula rasa when we're born. So it comes with its own point of view. And I will show two people. They are acting different than their brains. The first one is James Fallon. And if you have read this is his book. I think it comes, October 2013. For these neuroscientists I met, this one I interviewed with, I think it's like 3 or 4, 2015 or 16. The interesting thing is, with the James Fallon is, he's a neuroscientist, but he was working in this, like the book, he was working with the psychopaths. So at one point, he has to be the part of the experiment. He was looking, the experiment was, there were images, not the electrical signal, but the images of the brain, and they try to understand which one maps the psychopath. So the question is, if you look at the imaging of the brain, can we see if the person is a psychopath or not? So they got the images of the psychopaths, and they got the images of the control people, and control people in the experiments, mostly the faculties stuff. Okay. And so there's a blind experiment, so you cannot see the names. But at this point, James Fallon was looking at like this, categorizing. That's a psychopath, normal. And then he transfers the data, like the output, to his friends. And his friends came to him and said, like, did you check the names? Because normally the names are close. And he said, no, like blind experiment. And then he showed him some brain image, and he asked, like, what do you think about that? And he said, like, that's psychopath, like 100% psychopath. And then they opened the name, it was his. So he has a full psychopath brain, and that's like his book is about that personal journey into dark science. So as you can see, like I was talking with him about that, and you can see my face, I'm very happy. It's not like I'm talking with a serial killer person mind. So you see, his brain is actually telling that he's a psychopath. But because of the other influences, he becomes a neuroscientist, and he becomes a very good neuroscientist. He has TED Talks, if you have ever watched some of the serial killer TV series like me, you would know that because some of them are based on him. So that's something, like, that's the thing about the singularity. The singularity, you cannot find one brain that you expected it to behave the way you expected it to behave. The second one is Temple Grandin. That's a movie about her, and that's her TED Talk. So Temple Grandin, she was autistic. And she was born in a time where people, they don't know about the autism. So they diagnose it like the brain damage, because she couldn't speak until she was 3.5. And she cannot have a human contact, not even with her mother. She doesn't like to touch. She is full autistic. But then, as you can see from the picture, or if you watch the movie, Temple Grandin is a speaking person for the autism rights and neurodiversity. So she did many TED Talks. She is doing constantly talks. So the person who supposed to, from the point of view, who brain, supposed to not to talk with people, not to keep eye communication with people, she is doing the opposite. So that's why the brain has its own point of view. We cannot just looking at how it's wired, and we can make a decision about how it should behave. The things are changing. So if you were interested in the singularity, these are the two books that I can recommend. One of them is with neuroscientist and the mathematician. The other one is the neuroscientist. So they both answer the questions like why brain cannot be simulated by a Turing machine. So if you are interested in that, I will definitely recommend it. And the other thing, before we go to the last slides, I think you're done. Okay, so let's see if we can see that. Again. Okay. Let's see one more time before I do that. How was it?
Totally opposite than yesterday.
Okay, because yesterday she was so calm. I was thinking that she's going to be calm. Okay, so let's end this session and see her brain. Okay, so you're feeling, I would say, like that? Very relaxed? Very relaxed. I would say very relaxed. Okay, so now you see, to be honest, that actually, yeah, very different than yesterday, because we tried that yesterday. Yesterday she was very calm. And today, this is not her brainwave, by the way, so, but normally brainwaves look similar. This shows that how relaxed or how not relaxed her brain was. And you can see she's 45% relaxed, 45% calm. Yesterday it was about like the 70, 80%. And so in here, let's say if we zoom in, you can see that from the ups and downs. So the downs are the calm part, the ups are she's not very calm part. It's like, as you can see, very understandable. That's like being on the stage. It's not the calmest thing in the world, but for her, it's like very nice 45%. And you have like this, in the bottom, it shows like 12 recoveries, 38 births. 38 births shows that she is the most relaxed. And 12 recoveries means that she gets like the uncalm and then calm, uncalm, uncalm. So that is like, if anyone wants to play with this, I will be in NATO stand today, so you can just check how calm you are, especially the presenters, if you want to check it. So yeah, and that is normally your brain waves are also, let's say, more noisy than that. So like just the first part, I think I can, so take this first part and multiply it with this part, so that's how your brain noise is. But that's a very, as I told you, everything that you're doing right now, it's embedded in there. So the hard part is to extract it. And let's go back to the next one. Okay, next one is the last slide. So human 2.0 are coming, even if it is like the singularity or not. As you can see, wearables are coming. I know that a lot of you have already the watch as the wearable, but for EEG, Apple just had the patent application for the AirPod with the EEG inserted. So you can, with AirPod, you can even measure your brain waves in the future. And as you know, of the people from the telecommunication background, you know that the 6G era is coming in 7 years right now, 2030s. And the biggest, if you read the white papers, you will see that 6G is about the human technology interaction. And that's the time where we see the wearables more into our lives. And that can be anything like the prosthetic arm, exoskeleton, like I showed you at the beginning from the Giuliano Pinto. It can be exoskeleton. It can be bionic eye, bionic, like the hearing, anything. So, but just don't mix it with the Black Mirror movie, because as I explained to you, brain is a very detailed, like very complex structure. You cannot just say that, okay, yeah, we see the brain waves, yeah, we can extract it, it's like that easy. It's not that easy. So it's very noisy. It can affect, let me give you one example. We're doing an experiment, and during the experiment, the thing is, you have to keep your tongue at the place that you start the experiment. Because when you move your tongue, like one point that you're doing when you're speaking, it affects the brain waves. So if you cannot keep it in the same position, it's very hard when you are doing some mental experiment and you have to focus on your tongue too. That's very hard. But that is something, a noise in the signal. Yeah, for basic things like that, tongue movement, jaw movement, neck movement, we can eliminate it. But let's say if you have, when I ask you to make an experiment and then thinking about one thought, but at the same time you're thinking about the other thought, I cannot separate it. So that's why it's not very easy. If you follow Elon Musk right now, Neuralink, he's saying that they're making the human experiments and they're taking this outside, and everyone in the neuroscience tell him like good luck, because when the brain starts to move, it is not really moving as you expected it to move in the lab. So moving in the lab and moving at real life is a very different. So anything that you can do, I will say that the future is nice, but it's not a Black Mirror movie. So thank you very much. And if you want to play with that, I'll tell you, it's like I will be in the Atos booth. Thank you.